welcome to everybody that's here today to attend the webinar. The title of the talk that I'm going to be giving is The Mystery and Promise of Plasmonic Nanoparticles. I'm going to especially focus on plasmonic color, sort of the visual aspects of these particles, and which is really gives us a completely new and novel way to generate very intense and vibrant colors with a number of advantages over dyes and pigments. So first, as a brief introduction, NanoComposix itself, our mission is really to help people bring nano from the initial early stages of concept all the way through to commercialization. So if you're at the beginning of that process and you want to conduct research or build prototypes, we have over 500 different sizes and shapes and surfaces available for you to quickly get up to speed and get you started right away. If those initial experiments are successful, we can customize a particle type to your particular need or provide larger quantities for the material to work with. And then really our goal is to continue to help people and work with them to finish the R&D, build prototypes, and then ultimately scale to bring the material out into the commercial market. We're working with over 15 different startups right now and a broad range of exciting applications that have demonstrated both technical feasibility and the ability to meet cost point once it reaches market. So in terms of our world, this is kind of what we have for our expertise. So we're mostly in metals and metal oxides. So these are cores of golds and silvers, which are the plasmonic materials, and I'm going to talk a lot about that today. Iron oxide, to give some magnetic properties, titanium dioxide, which is photocatalytic and high index. We do a lot of work with silica as a spacer layer and as a way to get materials compatible with a whole bunch of different endpoints and resins. And then we have a slew of different materials that provide antimicrobial properties. And then on that core, we have different surfaces that we can put on, things that are covalently linkages to different materials, biofunctionalizations, different charges, different stabilities, all things that help with the integration of that core particle into some end application. In addition to just cores, we can also produce more complex materials where we build a shell around the material. That can be silica, that can be gold. Often we'll embed fluorescent or magnetic components into that shell, and we can functionalize that surface as well. And then in addition to spherical particles, we also do a whole bunch of different shapes. So hollows, cubes, plates, rods, stars, wires, and each of those shapes has a distinct reason why it's interesting. But today I'm really going to be focused on color, and this is kind of the world that we live in. Color is one of the main ways that we experience our surroundings, whether that's nature, chemical pigments, or through active displays such as monitors and TVs. And in order to understand the different ways of making color, we can kind of break it down into really two main elements. So this is sort of the basics of thinking about how we perceive color. So one's an additive and then a subtractive color. So in an additive process, you're creating color by adding light to a dark background. So this is, for instance, in your computer monitor, it's a black screen, and then it's backlit with some LEDs that are passing light through some filters to deliver a particular color. And in that color spectrum, we usually build things up through the red and green blue channels, and then that gets us our palette of what we see on the screens. A second way to create color is what's called a subtractive process, and this is where you are essentially putting pigments or dyes down on a white background to selectively block wavelengths of light. So the light's coming in, it's illuminating, it's being reflected off, and you're seeing all of the light that isn't taken away by the subtractive process itself. So what's interesting about what we're going to talk about today, which is plasmonic color, is that unlike dyes and pigments, which are really based on chemistry, and in order to change the color you need to change the chemistry, we're proposing, or we're working with a whole new way of generating color, which is a function of the material, usually these metals, silver and gold and aluminum, copper to less extent, and then the size and the shape and the local environment of those metal nanoparticles. And through that engineering, that geometric engineering, we can create this plethora of pigments that have very unusual properties. So how does this work? So the basis for the effect is called the Plasmon resonance, and this is essentially a collective oscillation of electrons at the surface of the particle. And one way to visualize this is to think about the nanoparticle as a metal with free electrons, and then as light comes by, light is just an oscillating electromagnetic field. So as that wavelength comes by, it's going to drive the electrons to one side of the particle, and as the trough of that wave passes, it's going to go to the other side. And so you get this sort of bouncing back and forth of the sloshing of electrons. And what's really special and unusual about silver and gold is it has this unique dielectric function that means that under certain conditions that are really limited by geometry in the material, that resonance or that sloshing can be very large. And the formula there sort of shows the polarizability, which is how we talk about the strength of that coupling reaction. And so when that coupling reaction is very high, the particles strongly interact with light, and you can get very intense scattering and absorption. So if you look at the chart below, this is a UV visible extinction of silver nanoparticles of different sizes. And you can see that as the sizes change, as it gets bigger, you start to get different structural features and different resonance, and is effectively changing the color of the material itself. So if we look at what this actually looks like when we're seeing things in solution, these are some images of gold nanoparticles ranging from about 10 nanometers up to 100 nanometers, and silver particles in that same size range. And again, looking at the UV vis plots below, you can see that as that size is changing, we're shifting the resonance, and we're getting a shift in the color. Going from a sort of a clear red down to more of a scattering pink, and then with the silver, starting with the yellow and moving more to an orangish hue. And what's interesting and important about this is that by knowing the theory behind how these particles are reacting, we can actually predict which color and which spectrum we want to target, and then we can just build that particle to create that particular pigment. The color shifts that we get here are definitely changing, but if we move to different geometries, if we move to particles that have more of an anisotropic shape, so these are some silver nanoplates, about 10 nanometers in thickness and ranging from about 40 to 150 nanometers in diameter, we can get much larger shifts all the way out, across the visible and out into the infrared regions of the spectrum. So we've, again, just sort of taking advantage of the material properties, the modeling to come up with a selection of particles that's going to be useful for future applications. So the thing that's different is that, what I showed you before, you could almost obtain something similar just by using a dye or a food coloring, but there really are some fundamentally unusual effects that come only with plasmonic materials, and one is what's referred to as a dichromic effect. So here the particles will actually look different depending on how they're illuminated. So the plasmonic particles are sort of accessing both the additive and subtractive color properties, and by building things of a particular size. So in this case, the silver or the gold nanoshells have an orange-brown reflection in scattering, but they're going to transmit a blue shadow. So I can kind of illustrate further how this looks by doing some sort of simple experiments. So here what we did was we coated some discs, some transparent glass substrates with silica-coated, titanium-coated gold and silver nanoparticles, and put them down on a thin film. And as you look at the perceived color, when it's on top of either a white background or background, it can be completely different. So with the silica-coated 70 nanometer silver nanospheres, it's sort of a dull yellow on the white, but then it comes up to this vibrant blue on the black. And if we have a higher index coating on that with a titania shell, we can get sort of an orangey yellow on the white, and then a green on the black. And then the gold has sort of a red color against the white, and then has almost sort of like a rust gold color coming back on the black. So very unusual in the sense that this would not happen with a typical dye. Typically you would just get a red that would look red on the white, and would sort of be a duller, barely visible red on the black. So the way this works, and this kind of comes back to what I was talking about before with subtractive and additive colors, is that we can kind of do a thought experiment about each of these layers and see what happens. So for the silica-coated silver, if we put it on a black substrate, what happens is you're illuminating with white light. A small portion of that light gets scattered by the blue particles and reflected back, so you see the blue, and the rest of the light is just absorbed by the black, so that's why it looks blue on a black background. And then on a white background, what happens is that you do get a little bit of reflection in the blue, but primarily most of the light that's coming back is reflecting off the white, and that's the green and the red, and that's what's giving you the yellow color that you see. So what that means is that you can get a really wide range of unusual optical effects that are changeable just by changing the geometry and changing the lighting of the material. So this is all interesting, except sort of a lot of this technology has kind of come around in the last 20 years, but in fact it's actually not that new. So if we look back to history, the Lycurgus cup, this is a famous cup that's in the British Museum, and it displays a different color depending on whether it's illuminated externally, which is on the left-hand side looking kind of a green, or internally coming out from the red and the purples. And this is gold nanoparticles that are embedded into this glass many centuries ago. Another historical example is in the stained glass. So a lot of the ruby red color that's in stained glass windows is actually gold nanoparticles. Some of the yellows are due to silver infusions. And so really these were sort of the first nanotechnologists back in the day, not really understanding exactly what was going on, but knew that that gold salts and silver salts in glass ended up producing these really unusual effects. So we come down to the promise of plasmonics. So this is really interesting. It's new. It's different, but it's also pretty expensive. So what is different about these plasmonic color versus pigments that's really going to motivate somebody to use this over a less expensive solution? And it's really kind of four things that we think about in terms of applications. We've got special effects, which are these dichromic properties where things look like different colors after depending on how they're illuminated and the background there are. There's a color permanence argument. So basically the gold particles never fade, even under intense UV light and heat. So typically with dyes and pigments, if you leave a sign out in the sun and it weathers for many years, that color is going to fade. So the gold actually gives us the opportunity to build things that never fade. Thousands of years of vivid colors, even under the harshest of conditions. So that's interesting for certain applications. And then there's a correlation to that, or a corollary, which is really the color instability. So in some cases, we can design these materials so that the materials themselves will react to the environment. And when they react to the environment, they have the ability to change their color and can provide us some feedback. And I'll give a couple of examples with that. And then the final example is that not only are these particles giving us color, but they're doing it in a way that's unusually strong. And they're strongly scattering or absorbing. And we can use that strong interaction with light for imaging and photothermal applications. So one of the first applications that we thought about from the sort of just visual sense, this was we were approached by Sofie Boons, who is a designer out in England, and we worked with her to kind of incorporate some of these nanoparticles into jewelry to kind of give these different optical effects. So here we worked with some gold nanoshells that were embedded in these polymer beads, and also some silver particles. And again, you see some very unusual effects in the fact that they've got these surprising shadows, in the sense that you've got this red material that's casting on a blue shadow, or you've got a yellow material that's casting a red shadow. We've also worked with and followed some of the art that Nichols has presented. So she has had an idea about using these plasmonic materials in art and creating different mosaics of color and pattern based on a single material, but with different sizes and shapes. And quite potentially, there's could be a whole field of plasmonic art in the future where you could get almost a photographic-like representation of an image with using a single material, which is pretty interesting. We've had projects where we've looked at coating surfaces. So these are some examples of different types of nanomaterials on some sort of metal blanks, and looking at the perceived color of the coatings. And again, we've got a permanence here. So if you want something that's going to last, colored but last for tens or hundreds of years, this is a way to do it. And another interesting angle is if you may want to be interested in coloring something without damaging the purity. So if you had a silver or gold coin that you wanted to color and keep your 5/9 purity, this would be a way that you could do it. In addition to permanence, we have the opposite, which is sort of the usefulness of color instability. So here we have particles that are reacting to the environment, and when they react, they give this visual shift. So this is a solution of silver nanoplates, and they start out in the blue, in sort of a blue color in solution. And then if you add a little bit of salt and you wait over time, what happens is you'll see a dramatic color shift, and not just from one color to another, but actually sort of tracing through this rainbow of different colors as the particles interact. And what's going on here is that the particles are starting out as these triangles or sort of high aspect ratio shapes, and you can see that on the right hand side. We've actually coated them with silica, so this is the silver is inside as the triangle, and this thin layer on the outside is the silica, and the silica kind of just slows this reaction down. Otherwise, this color change happens almost instantly. But when you add a salt, you start to etch the silver at the edges of the plates, and it starts to get smaller and smaller, reduces its aspect ratio, and it starts to look more and more like a spherical silver particle. So you're going from these triangular high aspect ratios to more sort of spherical-like particles, and you see this committance shift in the UV vis spectrum there in the plot above. A couple of applications, and so we were sort of brainstorming on why you might want to have these sort of exposure maps. One thought was that you might be interested in sort of time use history, so how, not if something has been exposed to water, but how long it's been exposed to water or salt. So this was an example where we loaded silver nanoplates into a foam and then exposed that foam to a little bit of salt. And we watched what happened over time in terms of going forward and seeing these color shifts come up as a function of exposure, and it kind of gives you a history of what was going on in that solution. The other concepts we've thought about is potentially using those in ambient air, so as a humidity sensor. And I'll show you the next slide of a company that we worked with that. And then one concept was to use this actually as a bandage indicator, so 24-hour color change over once it's on the skin. So this might give you an idea of when you have to exchange the bandage, or if you had sort of a nicotine patch that had to be exchanged, we could put these time indicators in order to make that happen. So. This was some data that we got back from a Japanese company where they infused silver nanoplates into a paper and then put this into their factory walls and watched the effect of this paper on humidity over a function of time. We saw the shift from this blue to this sort of clear orange as things went forward. Another application, and we talked about this a little bit more in our last webinar, is more in the biological space. So what I said before was that the particles are actually really efficient at extracting light. And so if you build a particle like these nanoplates, hit it with infrared radiation, it can heat up, and that heat can be used in a sort of a treatment and efficacious way. So one application that this company that we're working with, Sienna Labs, is on acne. So what you do is you take a very high concentration of these silver plates. They're actually silica coated. You rub it onto your skin. There's a sort of a paddle transducer that vibrates and massages those particles deep into the hair follicle. And then when you hit it with near-infrared light, you get this thermal injury zone in the sebaceous gland, and basically can permanently turn off nanoparticle, or turn off the oil production, which can lead to a permanent cure for acne. And so I actually just wanted to pause here where I was going to run a quick poll and see if you guys had any opinions on whether this is something that you would consider in terms of a therapy, and look at that. So if you should see a few questions, if just to get a gauge on what your tolerance is for this thing. We've done an enormous amount of safety work, but it would be interesting to see where you're at. So it looks like from the poll results that more than half would be comfortable if you had more information. A good percentage, 1 in 5, would have no fear and be able to dive right in, and then 20% were thinking a little bit skeptical, but might consider it if anything. So yeah, so so I guess what we've seen is that the safety studies have shown that the skin is actually a pretty good barrier, and that the ability to get even very small nanoparticles through that dermis layer is quite tricky. So it ends up being relatively safe, and then there's been sort of hundreds of papers on studying the effects of silver and gold nanoparticles from the nano safety side, and the general conclusion is that they're relatively benign materials. So we think that the risk is fairly low, but as always, it's best to be cautious. So in conclusion, I just wanted to sort of reiterate our mission here, which is really how can we help. So if you've got ideas in either they're on the research side or on the commercial side, we do have this library of materials and a lot of information on how to use those materials, how to integrate them, and how to functionalize them that we can help out with. We've got a whole slew of nanoparticle analysis here if you want to find out more about either our materials or materials that you've acquired from somewhere else. We can help with that. And then really our long-term goal is to link up and partner with people to do custom R&D and prototyping and eventually bring that out to scaled manufacturing. So we have a number of companies that are either in commercial right now or very close to commercial, where we're making things under sort of ISO 1345, which is the medical device regulations associated with building these types of materials and devices, and then the quality system regulations, which is sort of the GMT production. We've got a nearly newly built clean room, so we'll be up and going in another month and be fully certified and have a place where we can produce finished medical devices. So we're excited about that, and we're excited about sort of teaming with all of these people that have great ideas and just help them get to market. So with that, I'm going to open it up and see if there's any questions that people have, and I'll be happy to try to answer them.
Great, thank you so much, Steve. We're going to answer some questions today, as Steve mentioned, during that were submitted during the presentation. Just as a reminder, you can still submit questions through the question pane in your attendee control panel. We will try to get to all the questions in our session. If we don't, feel free to email us with the email address provided on the screen. Today, our first question comes from Darren. Their question was in regards to early on in the presentation, you had shown some vials, and he was wondering what the concentration of those nanoparticles were used. You had some gold and silver, and then some color and size comparison.
Right. So one of the things to remember when you're working with these plasmonic pigments is, while you're using gold and silver, which are very expensive starting materials, because of their efficiency, and their ability to so strongly interact with light, that you don't need a lot of them in order to produce a particular color. So typically our gold particles are about 50 milligrams per liter, and our silver particles will be sort of in the 20 to 30 milligrams per liter. So you need a very small quantity of these things in order to get sort of vibrant colors up in the 1 OD or more range.
Okay, great. Thank you, Steve. We have another question about if we have combined either silver or gold nanoparticles with carbon dots, not quantum dots, but carbon dots.
Yeah, so we haven't worked a lot with carbon dots. We have done quite a bit with quantum dots and with other types of small fluorescent particles. Typically, if it's in solution and you can have them in water, then there's all kinds of options for assembly. So if typically we'll do a charge interaction if we can make one substrate or one particle positive and the other ones be negative, and we've got ways of associating those at relatively high densities on the surface. And then we do a lot of work with covalent linkages. So as long as there's a molecular handle, an amine, a sulfur, or carboxylic acid, or something that we can bind to the particle, then we've got chemical methods of covalently attaching it to the surface to make assemblies.
Great, thank you, Steve. Another question today comes from Bonnie. Can you tell me about the plasmonic properties of gold nanocubes?
Yeah, so we make both silver and gold nanocubes, and they have a strong resonance. Their resonance is more complicated. They tend to have more peaks, and so from a straight up color pigment fidelity perspective, there might be other geometries that are interesting, but what's interesting about the cubes is their edges, both at the corners, because they've got a very high rate of curvature, so they're interesting from a either surface enhanced fluorescence or surface enhanced Raman. And then there's a lot of people doing work with cubes where they're using sort of the flat edge of one of the cubes to put it onto a surface, and it's almost functions as a patch antenna. And so you're very, very sensitive to anything that's in that junction between the flat edge of the cube and the substrate. And there's a lot of sort of exciting work that's going on in terms of making very ultra-sensitive sensors and other configurations that utilize cubes.
Okay, thank you, Steve. This question comes from Joseph. Do we make particles that are smaller than 2 nanometers in diameter?
Yeah, so typically the smallest particles that we make on the gold side are around 2. Below that, you get into sort of more the cluster realm of things, so that you can get either things with a distinct number of atoms, or that you have very strong ligands that allow the particles to be stabilized in that sort of 0.6 to 5 nanometer regime. So we certainly have done some custom work in that things, but we haven't had a huge demand for people looking at them as a sort of bulk substrates. But please contact us if you've got a specific size that you're looking for.
Great, thanks, Steve. That's really helpful. You also mentioned the particles for use in kind of these color coatings. I have some difficulty with proprietary coatings from other suppliers. Are you guys open about the type of coatings that you have?
Yeah, so that one of the decisions we made really early at NanoComposix was that since we were supporting the scientific community, that in order for them to really understand what was going on, it was important that they had all of the information. So typically we don't have any proprietary coatings. We tell people exactly what's on the surface, and then provide sort of an in-depth specification sheet that talks about all of the physical chemical measurements and solution properties that things are suspended on. So it makes it a lot easier to debug the science when we're open book, and I think that's been a good decision for us.
Great. I think that's, for now, that's the questions that I have from our audience. So I'd like to thank everybody for coming to today's webinar and participating, the mystery and promise of plasmonic nanoparticles. If you do have any other questions that we either didn't answer, well, we tried to answer everybody's question, but if something comes up after the webinar, please feel free to email us at info@nanocomposix.com. And on behalf of NanoComposix and our presenter, Dr. Stephen Oldenburg, thank you so much for joining us today. Have a great day.